I'd like to demonstrate how to solve two different kinds of relative abundance isotope problems for you. There is an equation that governs this kind of system. I don't really believe in the use of that equation. You're welcome to look it up and use it if you can make sense of it. But honestly, I think that you should just be able to reason out what needs to be done in these problems to get to the answer. So a few math things to watch out for. I'll point those out as we go. And you definitely have some experience with this kind of problem because it's the very same way that your grade would be calculated, I would think, in most of your classes. Because in most of your classes, your grade is actually a weighted average. Different kinds of assignments have different weights or different degrees of importance. So the first math thing I want to remind you of is that we never ever calculate directly with percent. We always use the decimal equivalent of the percent. So in problem 35, you can see that there are 4 isotopes of sulfur and their relative abundance is given in percent. So the first thing I need to do is to get rid of all the percents and go back to the decimal equivalent of each of these values. So that's accomplished by dividing by 100 or moving the decimal point back 2 places. So for each one of these, I'll write in the decimal equivalent. So now we are not going to use the percent for any calculation. We're going to use the decimal equivalent. Now we already know the correct answer to this problem because it's asking for the atomic mass of sulfur. And of course, that information is found on your periodic table. So here's the sulfur box with a mass of 32.1. So we're expecting an answer of 32.1 or something very close to that or something that rounds to that. Now, I'm not going to worry about the sig fig stuff here, folks. I'm just going to round everything off to a reasonable number of digits. But in the end, I am going to present my answer to 3 sig figs because that's how our masses are presented on the periodic table I provided. So if 95% of the mass comes from isotope 32, the first thing I realize is that the answer should basically be about 32 because 95 out of 100 versions of the atoms present here would be version 32. So it's really no surprise that the final atomic mass of sulfur is going to work out to 32.1. But let's continue the calculation. There's no formal name for the next column, so I'm going to call this points because that is, again, a reference to how you would calculate your grade in a course. So we need to take 95% of 32. So that's accomplished by saying 0.9502 times 32. And that gives me 30.41 points, let's say. I want to take 0.75% of 33. So 0.0075 times 33 is 0.25 points. And so on for the other 2 rows. 0.0421 times 34 is 1.43 points. And in the last row, 0.00017 times 36 is 0.006 points. So this isotope occurs in such a low percentage that its final influence over the average atomic mass of sulfur is quite low. All right, so now what we need to do is to take the points and sum them up. So 30.41 plus 0.25 plus 1.43 plus 0.006 is a total in the calculator of 32.096. All of our masses are to 3 sig figs. The 9 influences the 0, and we get 32.1. So that would be a classic calculation of a relative abundance problem. But I want to do a different kind of problem for you. And in order to do this other problem, I want to rely on what we learned in this problem. And the main thing to take to the next problem is this. The sum of the points adds up to the atomic mass. Right? The sum of the points from each of the isotopes adds up to the mass. So problem 37. Problem 37 deals with element Z. Now there is no element Z, that is a made-up element. Sometimes we also talk about element X. And what we know about element Z is that if it were to be on the periodic table, its atomic mass would be 37.94. Element Z has two isotopes. Now one of those isotopes is listed as Z33, and that isotope occurs 1.108% of the time. And the other isotope is unknown, but it occurs 98.89% of the time. What is the identity of the missing isotope? What is its atomic mass number? Now, the first thing you need to expect is, of course, that the atomic mass number is going to be a whole number. Atomic mass numbers for isotopes are always whole numbers. A whole number of protons plus a whole number of neutrons has to give you a sum, which is also a whole number. So our goal here is to do what we did in the last problem, and that is to take the points from the first isotope, add them to the points for the second isotope, and that sum should add up to the atomic mass, which in this case we know is 37.94. So that's the conceptual part to understand about this problem. Now there is some background work that we have to do, namely we have to deal with the percents. We never work directly with percent. We need to go back to the decimal equivalent. So two decimal places, 0.01108 and 0.9889. So crossing out the percents, so there's no chance that I use them. Excuse me. So we want to do what we did the first time. We want to take 1% of 33 and basically 99% of this other isotope. That's how we did the first problem. So let's see what kind of progress we can make. 0.01108 times 33. So here's now our points from the first isotope. 0.366. So the points of the first isotope plus the points from the second isotope should add up to the atomic mass. So far we have the points from the first isotope. Now what we don't know would be the points from the second isotope, and we can't calculate that the way we've calculated it in the past, because in the past we used the decimal equivalent times the atomic mass number, but the atomic mass number here is missing. But that's okay, because we have an expression that we can solve for an unknown. The points of isotope 1, 0.366, plus the missing points from isotope 2 should add up to 37.94. We have an expression with one unknown. We always solve expressions for one unknown. So we have to solve for x. So x works out to be 37.94 minus 0.366. And that missing value for x is 37.57. So the points from the second isotope is 37.57 points. So we know the points, but we still don't know the atomic mass number. So again, let's just think about what we've done in the previous two problems. What we did was we took the decimal equivalent of the percent, in this case 0.9889, we multiplied that by the atomic mass number, and that got us the points. Well, in this case, we know 0.9889. We do not know the atomic mass number, but we do know the number of points, because we just solved for them, 37.57. And once again, we have an expression with one unknown. So we want to solve for x. Now, solving this expression for x, right? What we want to do is divide both sides by 0.9889. So it's 37.57 divided by 0.9889. And the answer that I get in the calculator window is 37.99. Now, it goes on a little bit more, but that's fine. Now, getting an answer of 37.99 gives me a lot of confidence that this is probably correct, right? For two main reasons. The first reason is this answer is practically a whole number, and atomic mass numbers are always whole numbers. And of course, the nearest whole number here is 38, which is the answer. The other reason why this looks like the right answer is look at the atomic mass of element Z that we were shooting for, 37.94. It's practically 38. And this second isotope occurs almost 99% of the time. So is it any wonder that the atomic mass number of the most common isotope is 38, right? I mean, this is why the average, the weighted average, is shifted or skewed or so much closer to the 38 than to the other isotope of 33. So between these two approaches, you should be able to solve the remainder of the problems on this page.